Now we will be having a session by Dr. Shajahan Kutty on the topic of beamforming.
For cellular communications, as well as in certain niche type applications, including imaging, geophysical exploration and sciences, beamforming has traditionally been used. The difference is between modern day beamforming and the traditional beamforming techniques is uh, in the olden times, it was basically what is called as analog beamforming, which we are all familiar with. And modern day beamforming is largely digital beamforming. So I'll explain the difference between that as well. Uh, the demand these days when it comes to wireless communications especially is speed. Everybody wants fast download speeds, and if you just do a quick calculation, an uncompressed video transmission, as you can see over here, for a 1920 by 1080 HD type video transmission with 90 frames per second, and assuming a resolution of pixel resolution of or rather a bit resolution of 30 bits per pixel would require 5.6 Gbps. Of course, I'm talking about uncompressed video. But what this entails is the requirement of a very large bandwidth, which as on date for these kind of speeds is not available in what is called as a sub 6 gigahertz band, which is traditionally being used for Wi-Fi, etc. So the research community moved on to higher frequency regimes, and one such regime is what is called as the millimeter wave regime. And millimeter wave frequencies, theoretically speaking, span from 30 gigahertz to 300 gigahertz, but implementation wise across the world, it is from 24 gigahertz to around 300 gigahertz. Even India is looking at deploying millimeter wave for 5G, for example. 5G has two separate frequency ranges. One is below 6 gigahertz, which we all use, most of us use today. But there's another frequency range called FR2, which is in the millimeter wave range, which is about 24 gigahertz. And the reason is in order to support higher and higher speeds. Now, the problem is that these kind of scenarios, that is where high speed is needed for data transmission especially, you need highly directional beams. And what you will see in the future when it comes to modern day communication systems are antennas which will no longer be sectored, but rather they will focus their power, or they will radiate power in specific directions. And when I say specific directions, we all know that, for example, a half wave dipole would have a half power beam width of around 78.5 or so, but I'm talking about half power beam widths of like 10 degree, 15 degrees. That is what is being envisaged for very fine antenna beams. So as on date, the licensed bands for millimeter wave communications, that is high bandwidth, high frequency communications, are 28 gigahertz, 37 and 39 gigahertz allocated across the world. Of course, these are standardized in the sense that these are ITU recommendations. There are country-specific regulations as well, but the 7 gigahertz band from 64 to 71 gigahertz basically is unlicensed, and a very popular application is what is called as the 802.11ad wireless LAN, which is primarily used for short distance, that is for joystick, gaming controllers, etc. That is within indoor use they use it, and it's capable of delivering speeds of like multi Gbps. All this is possible because of millimeter wave communications. These are a few more specifics. As I said, across countries the location changes, but what we can quickly summarize here is that the 60 gigahertz band is the unlicensed band, is to be used indoors, and the 28, 37, 38 as well as the 70 gigahertz to 90 gigahertz band, which is used for automotive radars these days, is what is earmarked for outdoor type communications. Now, we all are familiar with this basic uh, free space loss equation, that is received power when you have LOS type transmission, that is outdoors, undergoes an attenuation which is of course directly proportional to the transmit power, that is whatever power the transmitter is capable of producing, depending on regulations or the higher limit of the hardware itself, multiplied by or it's inversely proportional to frequency, directly proportional to square of wavelength, inversely proportional to square of frequency. And we also know that it is inversely proportional to the distance, square of the distance. But what is significant here is that if we talk about millimeter waves, which are having carrier frequencies in the range of gigahertz or so, then what we are talking about is very high loss, because the received power would be very small, because received power is inversely proportional to square of frequency. So compared to traditional bands like your Wi-Fi unlicensed bands, we are looking at losses which are in excess of 20 to 40 dBs. And if you add a shadowing loss, that is loss due to objects, that is your signal bending around objects, etc., as well as signals which block your LOS. Similarly, penetration loss through materials and also human blockage, which is a big problem, because if you do antenna beam forming, the beams being very directional can easily be blocked by even by human beings, which whom basically are mobile. And then you add attenuation due to atmospheric effects, foliage, and ultimately if the antennas are not polarized, the polarization mismatch is there, then you're looking at huge losses. And if there is huge loss, what it means is the signal to noise ratio at the front end of the detector becomes very low, and we are talking about high speeds. So detection as it is a challenge to control the bit error rate. And if the SNR itself is very low at these high frequencies, then detection becomes a huge challenge. So what that means is we need to work out a link budget. So this is what system planners do, that is telecom system planners do. They consider the transmit power, whatever it is, whether it's regulatory or whether it's the upper bound is constrained by the hardware itself. If you look at the left hand side table, we have considered a transmit power of around plus 10 dBm. For Wi-Fi in India, the transmit power EIRP upper limit is around 30 dBm indoors and 14 dBm outdoor. So we have like taken it conservative, in the sense we are not driving it to maximum here. So plus 10 dBm of transmit power without antenna gain, that is if there is no transmit or receive antenna gain. If you want to transmit over a distance of just 10 meters with the background noise, that is thermal noise, being assumed at minus 174 dBm, and a noise, assuming that white noise is spread over 2 gigahertz, and taking into account the noise that is added in the receiver, which is the receiver noise figure, if you account for, we are looking at a deficit of minus 17 dB, provided we are using a physical layer modulation scheme like quadrature phase shift keying. Eventually, the type of modulation that you use will determine what is the kind of SNR you need in order to satisfactorily detect a signal. But if you look at the right hand side table, what we see is everything else remains the same. But what we are now pumping in is the additional power, which is due to beam forming. And you can see that there is a transmit antenna and receive antenna gain of 12 dBi. So most modern day beamforming systems will, I have read publications where they have gone up to around 25 dBi or so, that is additional gain due to beamforming. So even if I take a conservative 12 dBi transmit and receiver gain both sides, then we end up with a surplus of 7 dB in the same setting, that is the exact same scenario which was assumed without beamforming. So we are looking at not only compensation of loss, we are looking at increasing the signal to noise ratio, and eventually that means increasing the data rate. So the good thing about antenna beamforming in modern day systems is that since we are talking about wavelength of the order of gigahertz, and we all know that phased array antenna spacings are roughly lambda by, yes please. So manufacturers, that is over the equipment manufacturers basically have to comply to government regulations when it comes to higher limits. So if you look at Wi-Fi devices which emit power, including routers, etc., then depending on the technology, if it is 2.4 gigahertz, then the higher limit in India, that is country specific limit, is 30 dBm indoor, and the outdoor limit is 14 dBm. If you look at 5 gigahertz Wi-Fi, not 2.4 but 5 gigahertz Wi-Fi, then the higher limit is more. That is, it is around 23 dBm outdoor, whereas for 2.4 gigahertz it is 14 dBm, because at higher frequencies the losses are more. So that's the reason why government is allowing higher limits. So regulatory bodies will determine what is the emission limit, and it is usually given in terms of two quantities. One is effective isotropic radiated power, which I just mentioned, and the other one is power spectral density. That is per unit hertz, how much of power is allowed. So these are the two parameters that equipment manufacturers need to comply. So they will never tune their equipment to radiate more than that. So that is the reason why at higher frequencies you need antenna beamforming. The additional benefit of antenna beamforming is in omnidirectional antennas, power gets wasted in all directions, but at the same time, that same power being spread over a larger area can cause interference to other devices also. So this is a problem that is mitigated in beamforming because the power is focused on the desired user. The third benefit, and another important benefit, is you can have multiple beams being transmitted simultaneously, which means you can have multi-user type communication or multi-stream type communication. For the same user, you can have different streams. Either way, you are increasing your system capacity, that is spectral efficiency improves multifold. So let us quickly summarize. There are three main advantages of beamforming. One is increase of antenna gain, and so increase of coverage and better detection. Two is spatial multiplexing, that is using multiple beams and increasing system capacity and therefore data rate. And third use is basically in order to mitigate interference, that is focus the beam only to the desired user and create nulls in the other directions. We are all aware that cellular antennas, for example, modern day cellular antennas, they use a kind of a sectored pattern in order to serve users. So generally, until a few years ago, this each sector would be 120 degree and three sectors would usually be used. But modern day cellular antennas have started using beamforming, so it's no longer rigid. That is, the area served by each sector antenna is no longer rigid but flexible, because the beam widths are also flexible. Some of the terminologies, so we know that isotropic antennas basically radiate uniformly in all directions. So if you take a slice of cross section horizontally and vertically, you will get a kind of a circle. Half wave dipole along one of the dimensions, if you take the cross section, you get a kind of a donut type pattern with a fixed half power beam width. And a beamformer, on the other hand, gives you flexible beam width. Okay, so this beam, the beam can not only be steered in different directions, but the width of the beam can also be controlled. So that's the advantage over resonant type antennas. Of course, as I said, it gives higher gain. It can reject interference because it can focus the beam along specific directions and create nulls. We all know as communication engineers what's meant by main lobes, side lobes, and nulls. So sophisticated algorithms which run in the backend of this beamforming engines can create nulls in the direction of interference. and focus the main beam in the direction of the user. Then another thing is traditionally these cellular antennas which are used keep sending this downlink information to handshake with mobile phones, etc. So that is sent in a broad with a broad beam width, and that leads to wastage of energy because the user is located only at a particular location, and so much of the energy gets wasted. However, in beamforming, since you are sending the same downlink information in a focused manner, all the energy that you are using is completely utilized for transmitting that downlink information. So since this is happening periodically, this is not only happening when a user is making a call or receiving a call, this is a kind of a beacon that keeps getting transmitted regularly. With beamforming, that beacon energy being focused, the rest of the energy doesn't get wasted. So another important aspect of beamforming. Uh, since beamforming, you are capable of handling, let us say if you have n simultaneous beams, then you can have n different users being served, and so that means a system capacity increase of n-fold. SDMA of course stands for space division multiple access. So we are all aware of time division and frequency division and code division multiple access, but these days we also have what is called as space division multiple access, where the signals are confined in space, and so you can use that additional degree, the dimension of space, in order to do multiplexing. This is possible if you do beamforming. Another interesting aspect is beamforming can also mitigate fading. So we know that multipath fading occurs due to signal traveling from multiple paths. So if an intelligent smart antenna is capable of creating nulls in the direction of multipath, which causes basically fading, then due to the nulls, the multipath will not be received at the antenna. So another secondary benefit of beamforming is it improves signal quality because you are in a position to reject multipath by creating nulls in direction of multipaths. So all this, there is a lot of research and implementation. As I said, where is beamforming going to be used? So basically, indoor scenarios you are looking at replacing this Wi-Fi antennas with beamformer type antennas in order to increase system capacity and data rates. So next generation access points, Wi-Fi access points will be highly directional and serving users in a directional manner. Nowadays, there is a term which is called as fixed wireless access systems, wherein in a public space, you can access Wi-Fi that is free internet, for example. So access points for fixed wireless systems also are being deployed using beamforming, obviously to increase rates. So these kind of access points will be mounted on lamp posts and such infrastructure. In an outdoor scenario, in next generation cellular systems, you will see small cells and micro cells, femtocells, wherein mobile towers will no longer be the big huge towers that you see these days. So they will be like compact with less height. So since you are talking about high frequencies, it's easy to have this sort of small antennas and small cells which do beamforming, which is targeted towards users. Quickly, I'll just refresh our basic knowledge of phased array antennas, which is the mainstay for modern day beamforming. The idea is to have n elements, and these n elements have to be controlled. Of course, transmit power is going to be split into the n elements, and each element, the signal undergoes a different delay. In other words, the phase of the signal that is fed to each antenna element is controlled or shifted. And with this control, or rather with this delay, what you see is the signals that are emitted by the antenna will be shifted in phase. If you join all the phases which are same with that bold color line that you see, that becomes your wavefront. That is our definition of wavefront for electromagnetic signals. And an electromagnetic signal propagates always perpendicular to your wavefront, and so you can see that you can create wavefronts, and therefore the direction of propagation can be controlled, and therefore the direction of the beam can be controlled. The basic idea or the crux of the whole system is to assign different phase shifts to different antenna elements so that the signal undergoes different delays, and you no longer have a wavefront which is parallel to the axis of the, for example, this linear array. The wavefront starts getting tilted, and if the wavefront gets tilted, then obviously the direction of propagation also keeps on changing. So that's the basic idea. This, we have all learned this in our engineering, most of us, wherein we have done antenna theory. We have learned linear antennas. This is basically nothing but an illustration of that same linear antenna. So that's the basic idea in phased array beamforming. Now there are two types of beamforming configurations. Okay, one is called as a switched beamforming, which is called as a kind of a passive kind of a configuration, and the other one is an active kind of a configuration, which is called as the adaptive array. So in a switched array, this is a less complex system. So I said that you can create multiple beams in different directions. So switched array antennas, there is a resolution. What I mean is there is a fixed set of beams that your beamformer can produce. So you are not able to change the width of the beam or the number of such beams. And this is a simple system. It's called as a switched array system. As against an adaptive array. So an adaptive array dynamically or in real time can be steered. Of course, it doesn't have an infinitesimal resolution when it comes to steering capabilities. The resolution will still be finite, but definitely it won't be a discrete set of beams. What I mean is you should be able to steer the beam in any direction you want at any given point in time. So adaptive arrays are obviously more powerful because you have more control over where the power is directed, where to create nulls to mitigate interference, and also you can dynamically control the power of such radiation. The problem with adaptive arrays is, in order to do this, that is dynamic steering, you need a very complex system in place. Obviously you need an algorithm which is running in the background, and the most difficult part is, depending on the user or the channel, the beam needs to be steered, which means feedback has to come from the, that is, you need to take feedback from the channel basically, or the user movement. So it's not a simple system, it's a complex system with a lot of overhead, and there may be latency as well. So this is an example of a, like if you look at it from a pattern point of view, a switched array system. So here, like, we have divided the entire 360-degree phase into 16 sectors. So the beams that can be formed by a fixed switching system will only be this finite set of 16 beams or so. Okay, it depends upon what's the resolution. So higher the resolution, more will be the number of beams. Whereas adaptive arrays can create multiple beams. They can be steered in absolutely any direction. They can be steered in a manner that you can focus the power onto the desired user at the same time, that is simultaneously create a null in the direction of interference. So these are the true intelligent systems, so to say, compared to switched array systems. So these figures are basically from one of my papers which I published in 2020. I'll show you the front page of that paper as well. So this is well cited paper in IEEE Communications Surveys and Tutorials. So it's a 26-page paper in which all basics that you need for beamforming are explained, including architectures and implementations. So there are three main types of phased array architectures when it comes to analog beamforming. Sorry, two main types. So I think I'm going to use this pointer now, okay? So this first one that you see over here is analog baseband beamforming, okay? It's a transmit type beamforming. Of course, you can reverse it and make it receive. Your baseband signal is converted from digital to analog. Antenna weights are applied at baseband, that is analog baseband, and then you use an up converter, a local oscillator up converter, mixer, etc., and then power amplifier, and then each antenna element is fed a signal which is phase shifted. Uh, this this architecture is different from the second one because both are analog, because phase shifting is happening at the analog end. So in this case, instead of phase shifting at the analog baseband, you have phase shifting at the RF baseband. Okay, sorry, the RF, that is after up converting. So that's why the first one is called analog baseband and the second one is called as analog RF. The third technique is more popular these days. So this is called as digital beamforming. So you see that the antenna weights or the steering vector, as we call it, is applied at the digital baseband portion, which means that you need to have a dedicated RF chain now. The difference between these two is that in this you need a dedicated digital to analog converter for every single antenna element, whereas here you need a digital to analog converter which is common to all the antenna elements. So the question is, why make life difficult? That is why I have so many DACs, because DACs are power hungry. Similarly, when you are receiving, it will be ADCs, and those are also power hungry, power guzzlers at millimeter wave RF frequencies consume a lot of power, which is a problem. But why this is done is because these two architectures, that is analog architectures, don't allow for multiple beams simultaneously. It's not possible. As I had shown you the phased array fundamentals diagram, you could only generate one beam at a time with a set of weights. But in digital beamforming, you can generate simultaneous multiple beams because each antenna is being separately controlled. It's not a common control that you are giving. And this is achieved by what is called as pre-coding at the receiver at the digital baseband. You have a pre-coding matrix, and when you are receiving the signal, you use what is called as combiner. So pre-coding and combining in the digital baseband allows for multiple simultaneous beams, which obviously increases system capacity. So that's why this became very popular. But the issue was power, that is power consumption, and therefore they came up with a kind of a compromise between digital and analog, which is called a hybrid beamformer, which I'll talk about in a moment or so. So basically, adaptive system, that is, I'd spoken about switched and I'd spoken about adaptive. So you can see that in an adaptive system, unlike this kind of fixed beam systems, what you see is there is a feedback, that is the signal output is fed back to an error generator, and in order to train the weights, in order to dynamically steer the beam, I told you adaptive beam forming, you can dynamically steer beams unlike fixed beam forming. So initially there is what is called as a pilot transmission. The pilot transmission is some kind of a reference signal, and so using the reference signal you generate error at the transmitter itself, feed it to adaptive algorithm which continuously updates the weight vectors and makes that error zero. In a real life scenario, there won't be a reference signal. You will initially train it, but the moment when you go for live transmission and the error starts increasing, that's when the transmission is stopped, and then the weights are updated using the reference signal once again in order to synchronize or in order to mitigate the channel effects. And this is the reason why adaptive beamforming is adaptive, because it keeps on adapting the weights, weight vectors given to the phase shifters depending on channel conditions. As you can see, you need a complicated system for it. You need actually a processor, an algorithm, but the benefit is that it can correct for errors on the fly as against fixed beamforming, where errors also will remain fixed. So then the fixed, as I said, the fixed beamforming system will have fixed set of beams, but there is one flexibility which is possible. You can switch on and off antenna elements in a fixed beamforming system. So suppose you have 8 antenna elements. If you turn on all the 8 antenna elements, then very fine beams will get generated, very directional beams. But out of 8, if you switch off alternating antenna elements, let us say you are using 4 antenna elements, then a much broader beam will be generated. So one flexibility that is possible in beam switching systems is you can create wide beams or you can create narrow beams. But when you do this, wider beams will have less gain, narrower beams will have greater gain because the same amount of power is contained. The power density increases when you have less narrow beams. There is a procedure for this beam forming. So you start with what's called as beam training between the transmitter and the receiver. Once the optimum beam pair between the transmitter and receiver is acquired, you keep it as it is if there is no channel variation. If there is deep fading, you repeat training. And if there is slow channel variation, you go for another process which is called as beam tracking. So these are the 3 main stages of beam forming. That is beam acquisition, beam training and beam tracking. For example, if you look at this protocol, how to acquire beams. So let us say the transmitter has fixed number of sector level beams. So initially both the transmitter and the receiver will exhaustively search for the best beam pair. Once the best sector is identified, you will be refining the beams and then identifying the refined pair of beams. So this is the way things progress, okay, as far as beam forming protocols are concerned. These are some other techniques in order to reduce the computational complexity. I think that connection is a problem there down. Yeah. So these are other strategies. You can see that these are different strategies. In this strategy, you have sector level on one side and omnidirectional on the other side. Once you identify the correct sector, then you have refined beams on the other side. And then once you have identify the refined beam on one side, you have refined beams then on the transmitter side. Ultimately, all the techniques will give you refined beams at the transmitter and the receiver for communication. Okay. I think I'll skip this because I had already done this. Hybrid beam forming is a combination of analog and digital. So digital's problem was you needed DACs and ADCs for every antenna element. But in this case, what they do is they create sub-arrays. So while digital baseband processing is being done, that is precoding and combining is being done, you don't need a dedicated ADC or DAC for every antenna element, but a group of antenna elements will require ADCs and DACs. So hybrid, as the word implies, is a compromise between analog and digital where it combines the benefits of both. Of course, it also comes with disadvantages of both as well. So this is what is called as a hybrid array of subarrays, wherein you have one RF chain for a group of antenna elements. And this is the same hybrid beam forming structure, but the difference is every RF chain has control over every element. This has become very popular now because this gives better system capacity compared to making an array of subarrays. Some of the real world examples, this is you can see from many years ago. I was talking about analog or passive electronically scanned array antennas. So Patriot's Radeon system, okay, which was basically a jammer, basically a jamming type system, made use of the traditional analog type beam forming. Analog beam forming is there for decades now. The more recently, that is in 2005, one of the Israeli military systems, which is the active electronically scanned array systems, was one of the first fully digital array systems. And modern day, you must have heard about Starlink and the communication, the internet through satellites, etc. So more modern systems make use of ICs, okay, beamforming ICs, and these ICs usually are hybrid type systems which combines the benefit of analog as well as digital beamforming. I don't know, I mean, I'm not much experienced in ham radio, so whatever I could find, I'm just presenting over here. There was some kind of, I think you all have these contests, ham contests, and one of, in 2018, it's documented that one of the contestants had set up 4 monopoles in the 80-meter band, and they called it as the four square tower basically. And they so these were monopoles. So by having this variable length feeders for each of these monopoles, they managed to introduce phase shift, that is delays to each of the 4 monopoles, in order to create steered beams in 4 different directions. Apart from this, what I read was that they also had the flexibility to switch on and switch off antennas and test for directional beams using this setup. So since this is your 80-meter band, I believe it's 3.5 megahertz or so, right? So 3.5 megahertz. So that's the reason why you see antenna dimension being very high. Obviously, you can't use Yagi for such frequencies. So that's the reason why they use monopoles. Of course, the typical distance between antenna elements should be around lambda by 2 is the optimum distance. So you can guess that the separation of these towers will be around 20 meters or so. Okay, because this would be like lambda by 2 the dimension, and so d would be like 20 to 40 meters. Okay, lambda by 4 to lambda by 2. Then recently I came across documents in the US where they are thinking about using amateur radio for higher frequencies. It seems this is a band which is shared with astronomers, and so they want to protect this band for future use, rather than the millimeter wave guys or the communication guys taking it up. This is all that I could get for like ham radio, so please excuse me. Okay, I mean, I am more into signal processing or array processing for wireless communications. I'll end the session with a few modern day implementations, and I won't be specific, it'll be keep it general. So you can see that these are like 16 cross, that is 4 cross 4, so totally 16 elements, antenna elements, and this is an array of subarrays because you have one RF chain for every set of 4 antennas. A typical hybrid type setup. So beamformer ICs are usually fabricated in this manner, controlling a subarray of antennas. Uh, Typical building blocks in a beamformer antenna is your attenuator. So attenuator will taper your beam. Then you have the phase shifter providing the delay. You have a toggle switch which will switch between transmit and receive modes. For the transmit side, you have the power amplifier, and for the receive side, you have a LNA and another transmit receive switch for your antenna. This is we already know these things. Of course, the LNA is used for it's a low noise figure amplifier. Uh, so modern day systems, the passive electronically scanned array will usually have individual control. You can see this. Whereas the active one, you will have the transmit receive modules which are packaged together. Complexity increases here, but this is considered to be more power efficient compared to having individual chains for transmit and receive. This is how typically radiation patterns in 3 dimension looks like for a 16 element, that is a 4 cross 4. So typically this dimension will be around 5 millimeter by 5 millimeter. So I'm talking about modules which are nowadays used, okay, for beamforming, that is on top of wireless systems. The beauty of it is you can stack several such modules and you can do what is called as 3D beamforming. So beamforming today is being talked about in terms of azimuth as well as elevation. So that's the advantage of having IC based systems, because then you can design compact systems which can do 3D beamforming. And finally, like how we have traditional ICs, you have the option of having antennas on board, or you can have detachable type, or rather inline type packages which are embedded onto the ICs after the IC is fabricated, and then using wires or ducts the connections are made. So this remains the same when it comes to beamforming as well. I'll end my lecture with a few challenges that are foreseen in the use of this technology. So you have the LOS blockage problem as one of the biggest problems, because you're talking about highly directional antennas. So if at higher frequencies the propagation loss is more, so blockage effects become kind of enhanced or amplified. So human blockages, or for that matter blockages due to vehicles etc. in an outdoor scenario is a big issue, which can add to beamforming overhead and latency, as well as complexity. Then how to handle dynamic channel characteristics. So you need powerful algorithms which can keep track of the channel and keep on training the beams. Technology has not fully evolved, it's evolving, because the biggest challenge is spacing of the antennas and packaging the whole unit. We are now talking about 64 cross 64 antennas. That is the latest state of the art. What I showed you was a 16, that is 4 cross 4 antenna, 16 elements. Antenna attributes itself is a problem. How to maintain antenna pattern shape, directivity, how to maintain uniform gain. These are all challenges. And finally, how to manage interference. So the biggest problem is, though antenna beamforming can mitigate interference, but if an interferer is present within the radiation pattern which is beamformed, then for that the interference is more severe, because now the gain has increased. So this is another problem. To solve one problem, there is another problem which has cropped up. So how to manage that interference is also a challenge. So with that, I guess I'll end this talk and open it for sessions. Yes, sir. Yes, sir. Sorry? Yeah. Whether they use smart beams, I am not aware of that. No, I don't know whether they use beamform. Indian Ocean region. Okay, okay. I'm not aware of that, sir. Sorry. So one of the, I think,
Insightful session on beamforming. I request Professor Chetan Desai to give an memento to Dr. Shahjahan as a token of our appreciation.